Great. So our next speaker is Kai-Wei Chang, who is an associate professor at UCLA and has recently been working on multimodal language model stuff. So I'm really excited to hear about this.
Okay, yeah, thank you everyone, Staley here. Yeah, so today I'd like to talk about some of our study of how to combine vision and language together based on the transformer model. And I will focus a little bit more on how we can make sure those models can look at the detail and then align them well. So let me start with some motivating example. So this is my daughter. She is about 4 years old. So one of her favorite game during the driving time is like there's a book, and then when you click the book, it will say where is an elephant, and then she need to find the elephant. And I'm driving, so I cannot really, see these things. And but I will see sometimes she got frustrated, like she cannot really find where is the elephant, and she start to cry. And we say, okay, you can find the animal with this big ear. And then she say, well, no, that one is probably a rabbit, not an elephant, right? So basically, you're using some feature to describe in language to try to help her to identify that particular animal. So we can thinking about a more complicated example for the machine. So for example, if I want to teach the machine to recognize paramedics, right? So one way you can do that, you can collect 10,000 of an image and as a model look at all the image and to trying to generalize and find the paramedics. But I think the more natural way you can do is to describe what is a paramedics. And then you maybe, if you as a ChatGPT, you know what is this paramedics looks like, right? So you may have some patch or logo on their shoulder. They may wear some reflecting stripes so people can see them. They may bring some medical kits. So you would describe a bunch of feature, relevant context and things, patient, other things, accident. So then you will use all this information to recognize that particular image. So we started thinking about this problem since around 2018. Like, can we use a language to try to guide the model to understand the visual words? Yeah, so then we're going to talk about a bunch of the things that that we discovered along this way. But before I talking about that, I also want to show you, even nowadays, those big language models still have some limitation for some very basic things. So we find that, for example, if you have a mark under a table, a lot of time, even though a big language model has a trouble to recognize that because they mostly see a mark is on the table, so they don't expect there will be a mark under the table. And also, if you have a sentence with some negation, and many big language model cannot do that, and also for temporal or counting, those are things like vision language model, even with a very large size, still cannot achieve 100%. And this is, as you can see, we have a benchmark like ChatGPT, GPT-4 or Cloudy, Gemini, and for some dimension, they do much better than the smaller model, but for some of the dimension, they still not achieve 100%. Even this is kind of a simple question. Okay, so today I'm going to briefly talk about three things that we explore in this space. They are all kinds of relevance. So the first one will be the one as I motivate that we want to see if we can teach a machine using a language description. And then I will talk about a little bit on the other side that can we use a vision language model to do visual extraction. And then later on I will talk about how we can solve more complex reasoning problem like math reasoning problem with visual input. So since the BERT release, we started thinking about this problem. Can we train the visual language model kind of using this BERT structure? Yeah, and this is kind of pretty small and old model, but the way we do it is very similar to BERT. And I want to use this to get people into this space. So we know how people train the BERT model, right? So you will put a mass token and that model to predict what is missing in this mass token based on the context, and in that way the model can learn those correlations. So we can do the same thing for visual input. So you can give the image and then tokenize them as Luke talked about, right? And then you can ask the model to predict what is the word missing in the caption based on the image and the text. And in that way, because the model see the cake and then the model see the birthday, so they basically can associate some abstract information like birthday is associated with the cake. And you can also do this kind of sentence image prediction. So this is later on used, like people use like to train the click model. So you have a different captions, and then you're trying to see which caption is fit better with this image. And even with this very small model, we already see some very interesting things. For example, if you look at the attention the model have, you will see that there is an object 7, which is a car upside down, and there is an ambulance, and maybe a fire truck in object 9. And the model can actually learn association. The accident is associated with these two objects. So even I didn't explicitly tell the model, when there is an accident, the car will be upside down, but it somehow made that association. So fast forward in 2021, people are very excited about this clip model because you can simply just put a caption, say a photo of something, and by using this constructive learning objective, and the model will be able to use that to identify some new objects. And the way they do it is simply you can have a text encoder to encode these captions into a factor. And then you can also have an image encoder to encode the image into another factor, right? And then you have a bunch of factors represent different caption. You have a bunch of factors represent a different image. So if this caption is associated with this image, the inner product needs to be large, otherwise it needs to be small. So it's a very simple way that you can design this objective function, and then you can train a very good model. But later on, we find that even this model can do pretty well, but it cannot really capture some detailed description. And the reason is simply, people explore this in many different ways, and most of them are from the vision side. But we find that in the language side, it basically shows that it's almost impossible using this type of model to capture some detail. And the reason is that this text encoder is not perfect. It's very hard to actually let the model using just one single factor to represent a complex concept in caption. So let's say if I have some sentence, right, like a brown dog, and I can try to see that if I give that to a clip encoder, so it becomes a factor, and then I decode that factor back to the sentence. And we find that in many cases, the model will miss some detail, like maybe a brown dog becomes just a dog. And when you have a more and more complicated sentence, then you will see that the performance will be even lower and lower. So if you have, for example, just one object, usually you can do it. One object with some adjective, you can do it as well. But when you have multiple objects and multiple description, and the model starts to lose a lot of information. Okay, so just some quick quantitative number. We find that basically all these clean model, also some other sentence encoder model we can use. You mostly can recover about 30% of the information, and a lot of information will be missed from this basically encode and decode procedure.
Okay. What is percentage?
So this is an exact match. So basically, if the decode caption is exactly the same as the one. Yeah.
Maybe it's a decoder problem and not the encode problem.
Maybe in the decoder model problems.
Yeah. Maybe the problem is in the decoder and not the encoder.
Yeah, exactly. So one thing that we also try is that if you use more like C2C type of model, you don't encode the thing into one just single factor, then you can actually get around everything back. Yeah, but that's true. That it could be like decoder also lose something there. Yeah. Okay, but basically this kind of motivates us that the granularity of just matching sentence, caption, and image is probably too rough. You need to get some more fine-grained level of alignment. Yeah, so that lead to one of the model that we developed that we want to identify that particular object we mentioned in the image, and then we're thinking about that actually you can basically treat this as a face grounding problems, right? So you can put the object detection as face grounding, and then we can try to align the image and the text in the face to the object level. So let's say what you can do here is that I can collect a bunch of face grounding data. So in the face grounding data, I have an image, and the image was labeled with those bounding boxes. And then you will label that these bounding boxes is associated with certain faces in the captions. And then you can also generate some prompt. Basically, you can list a bunch of objects that you want to detect. And then if that object appears in this image, then you will associate them. Otherwise, they will be just matched to nothing. Okay, so using this way, you can use some existing phase grounding data like this one and generate some prompt using some object detection data. And then we can try to learn this alignment between phases and the objects. And in fact, you can just use a very similar objective like we do in the clip, but now just in the phase and the object level. Right, so basically you have all these prompt and you have all these bounding boxes, and then now you got this phrase embedding to represent each of the phase, and you got a bounding box, so you can actually get image embedding for each of these bounding box, and then again you can do this type of alignments. And of course, in this a little bit more detail here, that if you just do the alignment in the last layer of the transformer, it doesn't work very well. You actually need to do something even earlier. So you need to, for each of the layer, you need to do some early fusion. And then there's more detail in our paper. If you are interested in that, you can check that. Okay, so the interesting thing here is that we have a different type of image and text data, and then you can actually put all of them together into this joint framework. So for example, we have a bunch of object detection data. So those data, usually you have a very detailed, you have a lot of data, but then you only have a very limited category. For example, visual genome, they have like 1,000 category and they have a million of data points. On the other side, you have some phase grounding data. So you have a lot of phases that describe in the caption. So you have a lot of unique phases. But this data is usually much smaller. Like Flick 30K only have like 30,000 data points. So it's not like as large as those object detection data. But you can put them together and then train the model with both of type of data. And you can also scaling up the model by that the model do kind of a semi-supervised learning, or we call distance supervised learning. So you can use a model, look at the image and the captions, and that the model to first trying to identify those faces and the object in the image. And of course, originally the model may make a lot of error, but you can assume that if there is a caption, if this is a caption of this image, then most of the object mentioned in the caption will be appearing in the image. So you can use that kind of assumption to help you to train the model. So by this way, we can collect like several million of data points, and then you can train a relatively bigger model. And what interesting thing that we find is that compared with a supervised model, so this base model, die-head model, and if you train the model with one image per category, 3 images per category, 5, 10, until using the whole data point, you can see that the performance is showing like this red line. So our blue model with a similar size, even without training with any data point, is already achieved a performance similar to training with 5 data point. And with a few shot learning, the performance can be better than this supervised data. And then with this pseudo data I mentioned, and also with a larger model, you can get something in the purple line. Then the purple line, even without training with any of these training data, so this zero-shot performance is achieved something similar to you see 10 images per category. Yeah, and this database contain all these images that kind of have a very weird type of labels. So another thing that we find is interesting is that the model can capture some description you provide to recognize the thing you want to recognize. For example, if I ask the model to identify stingray, and stingray is not kind of a conventional fish, so the model doesn't see a lot of examples. So it identifies one of them but miss some of them. But we find that if you provide some description, say stingray is a fish that is flat and round, and the model now can do much better. Yeah, so that kind of exciting because that kind of we can see that we have a step toward the goal that we can provide some description and use that to recognize the objects. Okay, any questions so far? Okay, But then in the second part, we're going to show you that this model is still not good enough. And we still find that you cannot recognize, using the description to recognize more complex objects. So then move to the second part, that we find that, besides trying to align the model in a more low granularity, you also need to design some good fine-tuning method in order to force the model to look at the detail. So one thing we find is that if we want to really use the description and then teach a model to recognize that object in the inference time, the model needs to really understand those descriptions and capture the right thing. So what we want is that if I provide a description of this mallet, for example, then I say I want to identify the tool that has a wooden handle with a round head used for pumping and hammering, and the model should be able to recognize this hammer in this image. But if I provide something that's not actually in the image, like a tool with a long sharp blade used to chopping wood, usually this called like an axe, right? So this one is not in the image. The model should not recognize anything there. But we find that in the previous model I mentioned, the model cannot do that well. And in many cases, the model recognizes many other irrelevant things. And also when you have this confusable description, the model will still capture that things. And one key reason is that the model doesn't really capture those detail in those descriptions. And that is a problem we want to resolve in this work. Okay, so we find that there are two key challenges here. So one is simpler to resolve, the other is more challenge. So the simpler one is that the model actually didn't see a lot of descriptions of the object in the training data, because that's its nature, right? When we describe something to other people, usually you assume others know that things, right? You don't describe something like, today I go to a park, I see a car, and the car has 4 wheels. That's very weird. So you don't see a lot of those kind of description in the caption, so the model doesn't learn to capture that. But this one is relatively easy to resolve, because you can easily go to Wikipedia, you can use ChatGPT to generate a bunch of data. And then you can let the model generate those data, and then you train on those data. So follow that recipe. We build up a data set with about 10,000 phrases with all the description, and then use that to fine-tune the model. But the second one is more tricky. The second one is that the model doesn't incentive to really read the description. And what we found is that in many cases, especially for those models trained on the captions, if you already see that particular noun phrase, then you would just matching the noun to that object and ignoring everything like describing that objects. So in that sense, when you have a description, say there's a clown making a balloon animal, yeah, it can identify like clown. But when you say a clown kicking a soccer ball, it still recognize that clown, because he say, I know a clown, I know this one is the one you want to recognize. But it basically ignore all this description. So to solve that issue, we need to build some query that is more context sensitive. And this is actually very important. I will show you that it can be applied in many other cases later. Yeah. So in this test, we want to find the bounding box describing that particular object you are querying. So if the model don't know, or if you cannot find it, you will just report nothing, right?
What do you mean? Like, is it in its output distribution to report nothing?
Yeah. So basically, basically like this. So you would basically just not recognize any bounding boxes in the image.
So what's the underlining there? That's what you're supposed to find?
Yeah, so this is my input, right? So I give this input.
Why is the tool underlined?
Oh, where? Oh, the tool underline. I just want to highlight that word. A kind of tool. I mean, it's just a sentence, yeah.
But why did you underline it?
I just want to. So the tool is so like if the model recognize it is a tool, then you would put the bounding box and then put tool something here, yeah. But you can actually recognize, using any of these words and then find a bounding box and then tag with that words. Yeah, so that's my task.
I guess my follow-up is like, if you put a human and ask them, you have to pick something, put a bounding box somewhere, and you give them that description, but they have to choose, they probably would still pick that tool, right?
Yes, but I mean, the people can choose nothing, right? You can just say there's no bounding boxes describing this.
Okay.
Yeah, I mean, this test doesn't require you to really need to recognize a bounding box. It's not like you can put one bounding box, you can put 10, you can put 20. It's not constrained in a way that say you need to find one thing in the image. Yeah, and also technically, the way we really do that is that basically for each of the faces, you were trying to see if you can find a bounding box in the image, and if that kind of confidence score larger than something, then you will show that. Yeah. Okay, so yeah, so the way we solve this problem is that you need to build up some this context-sensitive query, and luckily this actually can be done by just query some of a language model. So you can ask a model to give me some tool that is confusable compared to mallet. So it will provide those description like X. And also you can ask a model to give me some context, right? And that is confusable. For example, instead of showing this teddy bear, you can say there is a polar bear. And all these constructive example can be generated by using a language model. Yeah, so you can basically query a language model and then generate a bunch of these negative caption. And then when you're trying to now do the alignment between this face with the object, then you face this situation. For example, in here, you have a two-word tool, but one with a description, they say it is a wooden handle with a round head, the other with a description, long handle, sharp blade. So one is aligned to this image, another is not. So that kind of force the model really need to capture those contexts in a way to distinguish these two, because they are the same word, but actually one is aligned, one is not. Okay, so that is kind of the key idea, and then we will apply this key idea in other places later in the talk. But we find that this is a kind of a simple approach can improve the model a lot. Yeah, so this is a bunch of a baseline, and then we participate one of the challenge in a CVPR workshop. That is that I provide your image and I provide some description of object with some specification. For example, I want to say I want to recognize the donuts with chocolate flavor. Then you need to identify those specific flavor of donuts. So in that one, most of the other vision language model doesn't do well because it may recognize all the donuts, not just the chocolate one. But the model need to really look at the specification and find that particular one that we mentioned. So with the base model, you got something like this is a average precision and bunch of different matrix. But you can see that with this description fine-tuning can improve the performance more than 10%. And there is still a gap to like 100%. So it's still a lot of things that we can do here. Okay, yeah, so just for fun, I have a demo in the Hugging Face. So if you are interested in that, you can try out our model there. So I put the image. So this is a student Howard who is doing this work, and this is a picture we take when he has a defense. So I put a caption here. The student with a flower bouquet pays his PhD defense. His advisor is standing on the right. So you can see that our model recognized him, probably not because he looks younger, but because like he has a bouquet and stands on the right. And another interesting thing is I recognize this a slide show is a PhD defense. Yeah, so showing this kind of a correlation between PhD defense and the slides.
If you have only a small mistake, do you expect the model to identify the object or not to identify? Meaning, like you give the whole description, but you say red instead of blue, or
I would expect the model don't identify because the model need to look at description carefully, right? And then if it is not really describing that thing, you should
100% accurate.
Yeah. Yeah, and in fact, the way that we generate this contractive data, a lot of caption will be generated in that way. You flip like 1 or 2 bits, right? And then the model will need to say, this is the right one, this is the wrong one.
But sometimes, like, you understand that you mean like a supervisor here, but you said like right instead of left. So you understand that there is something wrong in the description. But you say, for your task, in any case, you need 100% accuracy.
Yeah, I mean, at least the way I train the model, I expect that is 100% correct. But you are right. Like, as you can see, like a lot of the caption or the way we generate might not be 100% accurate as well, right? Because it's automated generate. So it could also have some error in the data.
So is paying attention to details a problem for image generation as well?
Yes. But the thing I'm talking about here is not about how to generate image, but yes, that is also very important. Yeah. Like if I want to generate, some particular thing with particular, outfit or something, then the model should be able to do that too, right?
Yeah, I'm just wondering, do you think it's easier to solve this using generative model, like directly drawing line boxes?
Yeah, it could be. Yeah, it could be. Yeah. Yeah, but in the next part, we're actually talking about like even for those large vision language model that any type of model, you can also using similar way to that model to look at more details. Yes.
So those numbers, I'm not familiar with the specifics. Are those like the probability that the model assigns? So then if you make a mistake or not a mistake, if you modify the description, and the probability that the model provides follows that change that you added to the text, do you consider the model noticing that change, or
yeah, that's a
like if it's going from 70 to 40, still putting the probability on it, but that change in the probability is because you added that model.
That's a very good question. That's actually something that we try when we do ablation study. So when you provide the accurate description, you can actually see this. Well, I don't know. This is kind of probability will actually get higher and higher. Yeah. So you can actually see that not only the model can recognize the right thing, but also in more confidence when you provide a better description. Yeah. Okay. Let me skip this part. Let me focus on the third part first. Yeah, so this is kind of for object detection model, but you may ask like for more nowadays vision language models solving more complex text, do we also need to do something to let the model focus more on the detail? So here, let me show you some cases where the current base of model still fail. So we know the model can do a lot of these vision question answering problem well. So basically I provide an image and I ask a question, like for example, give this image as what can we eat here? And the model can recognize this is a burger place and say, oh, this is a car hop surface and you can eat a hamburger there. But we argue that in many of these VQA tests, the model kind of cheating, because if the model just simply do OCR, right, and you can recognize there is a word hamburger there, and you can know that this is a place you can eat hamburger. You don't really need to understand the image, need to understand the detail. You can answer the question. So we annotate a data set that require a model to really understand the image in order to find the right answer. For example, here is a bunch of boats. And then each boat is a number with have some number, and then I ask get the number of the boat with 3 yellow and 1 red round item hang on it. Okay, so this one the model really need to recognize that particular boat and then find that okay, this is a boat the number. So we annotate the data in all different type of scenarios. So some of them require a model to understand and to do navigation, and some is more like sport or nature scene, and some is more like you need to understand the website or some chart or figure. And then we find that even those recent language big language model, they still not be able to perform well on this kind of tests. Yeah, and many of them is because the model don't really look at the detail of the image enough, so then it make a lot of mistake. And another interesting task that we are benchmarking and also looking at is that if I have some math problem that with some image input. So for example, I mean, this is kind of a typical thing that probably in your undergrad or the senior high school task, right? So I would basically ask, what is the size of the shared area under the curve? And then you need to recognize this equation, recognize this shape, and then calculate that shared under the curve. So for many of these cases, the model can give you a right answer, but some other cases it cannot. And then we do some detailed study, and we find that in many cases the model cannot. For example, you may have a mistake to recognize the equation, or you have a mistake to recognize some part of the image. And most systematically, we compare the human performance with model performance under different capability. When they're trying to solve these math problems. So on the left-hand side, we design different, so this is kind of different reasoning scale that we think the model required to have. Right, so to solve those problems, some problems need to have a geometry reasoning scale, some need algebra reasoning scale, some need to understand statistics, and some need to do some numerical common sense. And then this purple line is a human performance, and the red line is a GPT-4V model. So you can see that for certain dimension like logical reasoning and number common sense, the model is still pretty bad comparing to human. And on the right hand side, we have a problem with a different type of image. So some of them, the model need to look at the bar chart. Some of them need to read the table. Some is like puzzle test, or some is a natural image. And then again, we find that for some dimension, the model can do pretty well, like functional plot. But on some other dimension, like when you have a natural image, or when you have, for example, this one, abstract sim, the model cannot do very well. So then there's a question that how can we improve the model's comprehension of this type of image, and then let the model look at better on those details in order to solve those problems. Okay, so that comes to recent words that we published in New Rips last year, that how can we refine the large language model in a way using a similar way to do a description fine-tuning so that the model can look at the image detail. So the idea is kind of simple and similar to the one I would just describe. So you can first generate some good prompt. So you query a vision language model, say, please provide as much detail as possible to describing that image. And in most of the cases, the model can provide some detailed description, and then and those description would nicely describe what is in image. And now you can ask a model to suggest some perturbation of their captions, and then you can design different prompts. So the model can come up with a different way to generate this bad prompting, and also you can make this image more fuzzy, and then let the model cannot see all the details, so you will generate something wrong. Okay, and then once you have that, then you can now train the model with this image description, and then in that way, the model would, like previous model, will learn how to use that detailed difference to find the difference. Okay, so basically that is a kind of two-stage approach we have. So first, generate some good and bad prompt, and then you can apply the preference ranking method to let the model learn the difference between these two. And then the second stage, which would be like training the model by seeing those captions. Okay, let me provide a little bit more example here. So for example, here is an original image with someone playing, I think it's a ski or something like sport, right? So if you ask a model to generate a good prompt, then it will give you something here. So basically, a pretty well describing captions, like describing that image. And now you can ask the model to generate some bad prompt and generate something like similar, and then the model will generate a few kind of bad description that doesn't well describe that image. So, for example, the model may say there's a group of tree, but the tree is not there. The model, may say it is a snowball, but this is actually not a snowball. And then now you can basically treat this as a preferred caption and the rest as a dispreferred caption. And then you can let the model to use a preference ranking to update the model weight in a way that the model will more favor the first one comparing the rest. And this way will force the model to look at the detail of those captions. So one tricky thing we find that is that you also need to add in some regularizers here. So basically, when you do this preference ranking, it's important to also let the model to update with this preferred data using the language model loss. Otherwise, a lot of time the model will just go crazy. Okay, so with that, then you will be able to let the model look at better at the detail. And the second step is relatively easy. You basically just need to augment those model descriptions, image description with your prompt. And so then the model would train to solve the problem with the image description. And in that way, the model can learn to use those detailed description to solve the problem. And by doing that, we find that we can improve most of the model by 4 to 5%, over like several different benchmarks. Okay, so that is kind of thing that we can use this description fine-tuning idea to force the model looking at better at the detail, and then you can use that to solve a bunch of problems that require visual understanding. And more recently, I know everyone here is interested in reasoning, so we're also interested in reasoning, and we want to see that can we incorporate the reasoning path from model like R1. And so that we can let a vision language model can also capable to doing reasoning, and then improve the performance compared with some larger model. So we find that by using some simple trick I will describe in later, you can see that we built out this model called OpenVLThinker based on the Owen 2.5 VL model. And we find that by using those tricks, the model can actually outperform GPT-4 in some cases. So the way we do it is that so the DeepSeek R1 can provide you a bunch of reasoning path, but the DeepSeek R1 don't have a visual understanding capability. So basically, it can only do the reasoning on the test side. So then the question is, how can we collect those kind of reasoning path and then use that to fine-tune the VL model in order to teach them to do reasoning? And the way we do it is like you can first basically build a caption model like the one I described before. And then you can ask the model to generate the detailed description and then provide all the information in the image. And then the model will give you those captions. And then you can feed these text data into a DeepSeek R1 model. And then the model can give you the answer with this reasoning path. Right? And then once you collect this data, then you can use that to train your vision language model. And then the vision machine learning model, like training on this reasoning path, hopefully can learn how to do reason and then perform better. Okay, so that sounds good, and we try it. And unfortunately, the performance actually dropped, not improved at the first try. Yeah, so this red line is the base model we use, which is an Owen 10.5 VL model. And when we fine-tune on this reasoning path, the model actually dropped performance from around 68 to 62. Yeah, and compare with, this is a bigger model and this is some other baseline. So what's going on here? Yeah, so I think one of the reasons is that adding this reasoning path, basically the model doesn't really adapt well, and then and also the problem in vision language is slightly different in the original math reasoning problems. Yeah, so you need to do a little bit more than just do this fine tuning. So what we find what can work is like you need to alternatively between training to follow this reasoning path and also do some IL training itself. Yeah, so what we find what is working is that you need to let the model to do something similar to in the deep sea, that you need to using IL and GRPO to update the model based on if you can find the correct answer in this vision language task, and then go back to generate the corresponding reasoning path using R1, and then fine tune the model on top of that. So basically, you need to switch between doing behavior cloning on this reasoning path, and let the model try itself to how to do IL in the vision space.
Question. So this is by iteration. Do you mean like one batch, or do you mean like a whole bunch of batches in that, and then a whole bunch of batches?
So yeah, we do the whole bunch of batches. So iteration, one model by one model.
So bunch of batches for GRPO, bunch of batches for SIM.
Right. Yeah. So one iteration would be like training the whole model, and then based on the new model to generate GRPO and so on and so forth.
But you continue training with that same model.
Right. Yeah, so if you do that, then you can see that it gradually recovers its performance, and at some point beat the baseline model, and even achieve the performance similar to a larger model. Okay, so this is a thing still working in progress, but we put the paper on archive, and hopefully we will be able to achieve better result later. Okay, so yeah, maybe let me stop here. Yeah, so basically we believe that if you want the model to solve some complex tasks, you need to be able to look at the detail. And we find that doing instruction fine-tuning to that the model can generate a helpful caption is important in order to achieve that. Okay, so thank you everyone.
For your OpenVLThinker model, reasoning chains for your OpenVLThinker model. Do you have them?
Yeah, we have reasoning chains. Yeah.
Do you have some examples?
Here is some. This is kind of an example.
Oh, but this is not from the visual task, right?
This is actually from the visual task. Yeah, because we convert the visual task into the text.
Oh.
Yeah. If we have time, right? If we have time for more questions.
Yeah.
Okay. Yeah, so I'm trying to understand this. Can the model point to, as it's thinking, how does it refer to the image?
Yeah. So currently we don't really have a vision language model that have that. Yeah. So now we basically do this like iteratively. Yeah. But of course, I think maybe a better way, maybe Luke can do that, is like to incorporate this reasoning, scaling method directly into the vision language model.
Yeah. Some way probably to have a bounding box and look at the bounding box.
Right. Yeah, exactly. I mean, that's the thing that we want to do, that actually the model can, like human, right? You would scrabble something and then solving the problem. Yeah.
It seems to me more broadly, thematically, we are using language models and trying to distill some of the information to a small-sized vision language model.
Yeah. Yes.
Then if we change the setting to a very strong DeepSeek model, but that has access to vision, then how does all of this make sense? Like the DeepSeek itself has access to a sort of image and vision component. Then it can do the reasoning and it can do all the natural descriptions and so on, right?
Yeah, this is a good question. So I think there are two ways you can get a good vision language model that can do reasoning. Right? One is like distillate, like what I did, distillate the reasoning capability into existing vision language model. But you can also do like making the DeepSeek model, language model become any-to-any model, right? So you can do both. But the second one, you probably need a lot of compute in order to really train that model.
really cool talk, and I'm super bullish on like multimodal synthetic data in general. So I love what you're doing. How much do you think the quality of the captioning, matters? I mean, captioning's gotten really good, but it still hallucinates. There's still weird stuff going on, and you're asking for like paraphrases, and maybe some of those are actually okay, even though you think they're negative. Can we know, like, if you had a perfect captioner, how much better would it get, or how much is this actually hurting you in practice?
That's a good question. I don't have a quantitative number for those benchmark we have that if you have a perfect caption, how much we can get. Yeah, but in the error analysis we see a lot of error come from, you don't have a good caption. Yeah, but that's a good question that we should check.
Yeah, I wanted to do more work on like bootstrapping sort of captioning and image generation jointly. Right. It's hard.
Yeah, that's hard. That's right. Okay. Okay, and thank you everyone.